Dear learners, welcome back. It's week 3 of machine learning, and this week we're going to cover two different algorithms. They're going to be naive Bayes and k-nearest neighbors. Now these are both very important yet simple to understand learners that are deployed in real-world situations. We're also going to look at particular background information that's going to serve as fundamentals and foundations for your subsequent learning in upcoming weeks. They're going to include cost functions, which we're going to cover at the beginning of this pre-lecture. Now, as we do every week, we're going to recap what we learned last week, and then we're going to forecast what we're going to learn this week. So last week we touched upon concept learning. The idea of concept learning is to learn a concept. We can think of a concept as a type of function, right, that decides whether instances are part of that concept or not. Right? So we could think of, in the case last week, whether your friend likes a particular Singaporean drink or not. We observed this through a set of instances, data examples that were deemed as appropriate or disliked for a particular concept. We saw that we could start with the idea of concept learning as a search through script age or a hypothesis set. And a hypothesis set is specific to a particular learner. Each learner makes some assumption of what type of hypothesis set is suitable for it. For example, in the concept learning lecture, we assume that the concept learner has access only to conjunctive hypotheses, that is, hypotheses that are conjunctions of different attribute values. We also talked about the idea of a ordering of the different hypotheses from general to specific. So general ones encompass more instances as positive, where specific ones admit fewer instances as positive cases. After looking at the FindS algorithm, we agreed that probably we could use a more general algorithm, such as the candidate elimination algorithm. This algorithm uses the ideas of boundaries between S and G, where S is a specific boundary that only admits the positive cases as narrowly as possible as instances that are part of the concept, where G assumes that only the negative examples are excluded. So we can think of the boundary of S and G as being sandwiched between each other and then narrowing the space between them so to get to the target concept. So this space in the middle we called aversion space, all of the different hypotheses that might be suitable as the actual target function. We also saw that we can actually use an active learner to query that space. When we have many different hypotheses in our hypothesis space, right, our version space, we can pick one of them to query or an instance to query and try to eliminate some of the possible hypotheses in the version space to narrow down our search. Very importantly, we also looked at inductive bias. The idea of inductive bias is to understand that all machine learning algorithms have to have a bias towards what they consider as part of their hypotheses or not. Without this, it's impossible to learn because when we're faced with an unseen instance, there's always the possibility that that unseen instance is part of the concept or not. And if we don't make any a priori assumptions about what is considered in the concept, we won't be able to decide between these cases. So now for the forecast. This week we're going to look at Bayes' rule and show how it admits the possibility of learning from it using an idea of naive Bayes, which has two parts to its name and is very telling. Secondly, we're going to look at distance metrics. The idea of k-nearest neighbors allows us to measure distances from between instances and declare whether an instance is close by or far away from another instance of a different class. We're going to look at the training and testing times for both, as these considerations are very important for machine learning. And separately, we're going to look at a bunch of background information. Smoothing has to deal with naive Bayes and handling zero probability cases. But more importantly, cost functions, which we're going to cover in this pre-lecture, give a better idea of what's going on when we think about optimizing a learner for different parameter settings that it might have, all of the thetas that we saw in the first lecture. We're also going to view targets as a probabilistic example instead of thinking of them as fixed concepts. And finally, we're going to look at the curse of dimensionality. The curse of dimensionality basically says that when we raise the number of different features or columns that we have to describe a particular example or instance, it becomes more difficult to calculate the similarity of instances. And this affects the performance of learners when we go to high dimensions. Okay, so that's it for our recap and forecast. Shall we get started now?